All right. So today what I have is a GPU cooler for NVIDIA Tesla graphics cards that I've been designing in a couple of iterations over the last, I don't know, 6 months, but then recently um, did a total redesign, and that's kind of what I'm presenting now. So this is the cooler. Um, in all its glory. You can see there's a Raspberry Pi Pico running MicroPython. There's a bunch of MOSFETs driving 3 fans. Here's another shot from the back. So the reason I had to do this redesign was because in the situation that it's going to be installed in, there's now 2 graphics cards here. In the initial version, there's only one. Here's another quick photo of the design. You can see the controller kind of sits on the side of the manifold there, and then the fans are on the back. So here are the 2 cards installed side by side. Here's another shot of that. So there's 6 of these 28 millimeter fans, or 40 millimeter fans, sorry, 40 by 40 by 28. You can kind of see it here. You can see it better in another picture. So the way that I'm doing temperature feedback is I have these 2 little thermistor cartridges that are bolted onto the side of the graphics card. So you can't really see it, but these cards, the K80s, are actually 2 graphics cards, 2 logical graphics cards on a single like GPU kind of slot style regular card. I don't really know how to describe it. So there's 2 graphics cards on here, and there's 2, when you plug it into the computer, there's 2 visible to the OS. So the way they're designed, right, it's like this big long thing. So this graphics card is always going to be sucking up the air from this graphics card. So this is kind of what I call the hot side. So the thermistor is placed above the hot side because that's kind of the temperature you actually care about, the temperature that's always going to be higher than the other side. Here's another close shot of the thermistor. So this is getting into some of the earlier mechanical designs. I actually couldn't find a great hole pattern online, so I had to spend some time kind of with the calipers getting that spec'd in. You can see here the first design wasn't meant to sit in a case, in a chassis. It was just sitting on my bench, the motherboard like that. And I used these blower fans. So these are originally for a 3 printer, my Prusa Mark II. I had one of them fail, one of these style fans fail on the printer, and came in a pack of 6, the replacement. So I had 4 replacements sitting around, and that's what I did for this first initial approach. You can see here actually I'm powering these directly from my benchtop power supply. Here's the version 2. It was installed in the same configuration, just sitting outside of a case. But this time I had a little bit more control electronics. Not really, right? So this is just a buck boost converter that I was using to vary the voltage presented to the fan, but therefore vary the speed. Again, hacked together really quickly. Not really any thought put into this design. Here's the 3rd version. It's curved, so it's the same model as this one, but I just curved it around at a right angle so it could fit inside this case. Same control electronics as before, etc. Actually, I have another picture of this here. So the problem with this design, this approach in general, right, is these blower fans are very weak. I think it's like the unit of the way you measure how strong these fans are is like cubic foot per minute of air. These fans are, I think, 2 to 5 cubic feet per minute of air they can move. They spin at like 1,000 RPM. These little ones can do 30. One of these can do 30 cubic feet per minute, and they spin at 9,000 RPM. So it's significantly more airflow. So what I would do to get around the thermal problems that the original design would cause would be you can control how much power is presented to the GPU. So I was just throttling down power to get them to operate cooler and not crash all the time. So another goal with this redesign was to be able to operate at actually above their default power rating. So by default, the cards can consume, I think, 125 watts of power TDP. And then you can, in the software, you can tweak it to push that up to 175. So that was the goal of this design, was to have them be able to run at 175. Alright, so that's the images. So let's pop into CAD real quick, just to get a better view. So this is the manifold. This is kind of the main part. So there's not a ton to it. The core part is this loft. So if I step the design back, actually we can do, yeah, let's do this. So it's this really thin-walled thing, and then this loft. So the way that this loft is defined, the curves are splines that you can just select one by one to add into the feature, but the positioning, which actually, is that file open? I might need to open that file really quick. Oh, I want to hide those in the full thing. The positioning is defined by another assembly. Let me open that really quick. Which was a technique that I used in an earlier approach as well. So having a separate assembly for positioning the component parts, and then having a spline, or a loft rather, to, yeah, here we go. Having a loft to like join the two parts. Where is this file? Alright, so, okay, here we go. Interface fitting. So, if we hide the resulting manifold, so this is how the part is kind of drawn. So what I do is then, so you could, these parts are positioned with a bunch of mates, angles, and distances, and then you can actually update these values, these angles and distances here, and then get SolidWorks to spit you out a new model, which is like super useful. It was very, very helpful in prototyping. I don't have to, like, every time I wanted to make a change, I don't have to like remodel each of these curves, right? I can just update that assembly, hit the stop sign button, hit the rebuild button, and then get a new part. So outside of the different fans, it's a lot more compact. I also was able to make the walls a lot thinner. These curves provided a lot of strength in the part. The earlier designs were obviously overbuilt, and so these walls are really thin, which ends up, like, the printing time for this is on the order of hours rather than days like the other ones. So the last thing I want to show for CAD is a comparison of the different versions, just to get an idea, seeing them next to each other. So here's V1, and then V2 and V3. You can see that, yeah, there's a big improvement for each iteration, right? Not to say that these didn't work, but, you know, I'm still glad to have finally settled on this design. Alright, so that's it for mechanical. Manufacturing wise, I'll pull the photo back up. So I printed the parts on, like I said, my Prusa Mark II in white PLA. I found that even though PLA is usually not the greatest thing to use for temperature sensitive applications, since there's active cooling of the part in a way, it hasn't made a difference at all. Haven't had any sag or melting issues with that at all, because the parts are actively being chilled, right? Even on the earlier designs, same story. PLA is fine for this, turns out. To keep the PCB in place and keep the fans in place, I had threaded inserts, but I don't know if I have a photo of those offhand. Oh yeah, also, earlier on, to like kind of test things out, I had a one fan configuration of this as well. So I designed this plug that was useful for testing initially. Figuring out which fans to use was kind of tricky. I ended up just picking the most powerful ones, even though they're quieter options, just because I wanted that extra headroom to be able to eke out as much performance as possible. Because I did find that spinning the fans down did significantly decrease the noise. Like right now, you can probably hear it in the background, but I actually have it all running. So these are under full load. It's pretty loud, but idle is actually like very tolerable. Alright, so let's switch over to electrical, or try to switch to electrical. Alright, so this is the schematic, pretty much as basic as possible. It is 6 NMOS drivers, 1 per fan, all the same parts. It's these FQP30N06L. I think they sold these on SparkFun for a long time. I have a ton of them in stock. I was able to do this whole design without having to buy anything new, which was great outside of the fans and the graphics cards. And then there's 2 10K 3950 NTC thermistors. So the thermistor package is a little metal can. I actually should zoom in on I have a photo of that. Yeah, it's a little metal thing, a little metal can that has a thermistor in it that's then read by the Pico. Whatever. So, alright, so that the electrical is very simple, which is cool. Oh, there's the, oops, I had that open. So software is where it really kind of gets cool in my opinion. So let me switch over there. So turn the network camera off for now. So this is the interface for the Teslas. So I have 4 of them. Like I said earlier, 2 logical cards per PCI slot. So 0, 1, 2, 3. So these two are the back card. So there's 2 graphics cards there. So this one corresponds to these 2 cards, and the other one corresponds to the other 2 cards. So this one, you can see the temperatures are a lot higher. It's because it doesn't have this like big area. Like this card has all this surface area to dissipate that extra heat. But this card doesn't have that because it's parked up right against another graphics card. So this one is significantly hotter. The other thing worth noting, right, even within the cards, so this GPU is hotter and this GPU is hotter, and that's that hot side, cold side I was talking about earlier, right? So as the air moves through the system, like this side of the card is always breathing fresh air, and then this side of the card is always breathing warm air. So that's the distinction there. That's why the temperatures are so different across the 4 cards. All right, so let's get into the software a little bit. So I'm using the Raspberry Pi Pico. The cool thing about that is you can use MicroPython, which has been just amazing. I've really enjoyed developing on MicroPython. Lets you do a lot of really cool Python stuff in embedded world. I mean, I've done a ton of Python development professionally, hobbyist level, but obviously Arduino is king for like DIY embedded stuff. I really think the developer experience though with R shell really can plug in anywhere. I'll show you a couple cool things for that in a sec, but kind of getting to the core of the software design. Let me zoom in here. There are 2 timers that we configure in software that map to this callback. So this is a function that what it does is read off the current temperature of the GPU and then set the fans of the associated cooler to like a given speeds, right? So the way the speeds are calculated is really cool too. The idea, I wrote an algorithm. It's in this code. You can check it out. Where is it? So it would be this power function. So there's a power function which is exposed by this cooler manager object. The power function takes a float from 0 to 1, 0 being slowest speed possible, 1 being fastest speed possible. So that way you can have different types of fans that implement this power function in a different way, which is cool. So the power function, right, so how do you ask for 100% of 3 fans? You would have all 3 fans turning on all the way, but how would you have 50% of 3 fans, right? You could do it a number of ways. You could have 1 fan full blast and then 1 fan half speed and 1 fan off. You could do the 3 fans half speed. A number of different ways you can implement that. So the way that I did it was using a thing called or a number partition. So basically, the idea is to take the different possible fan speeds, right, get a cumulative value. So say you want to drive the whole cooler at 50%. So if you were to drive each individual fan at 50%, you'd get like a value of like 150 total percent that you need across the 3 fans. So then it takes that 150% number and splits it up as many ways as possible. So how many numbers can add to 150? How many combinations of 3 can add to 150? So you could do 10, 40, and 100. You could do 0, 0, or 0, 50, 100. You could do 120, 20, and 10. So it makes all these different combinations and then ranks them by loudness. So the loudness score is you take across the 3 fans, pick the lowest across the 3 values. You pick the lowest average value, or not the lowest average value. You pick right, okay, so the way it works, sorry, it's not lowest average value. Average wouldn't make sense. So it takes each of the potential fan speeds. So we have this file, fan constants, so different duty cycle ranges. And as an individual fan, as a potential value moves up this rank, it becomes more expensive. So a fan spinning at 4,000 duty cycle, which is like the PWM duty cycle, that is much less expensive than a fan spinning at 60,000. So what it does is take each of the potential combinations, so say, and then score them on how expensive the combination is, and then picks the lowest scored value. It's kind of a roundabout way of encoding the behavior that we want, right? Which is the quietest but most powerful drive speeds for the fans. So this is all going to be on GitHub. So if you want to check this out, you can. There's a couple shortcuts I had to take. It turns out that integer partitioning thing is a known, like, very hard computer science problem, and it doesn't help that I'm on an embedded processor. So there's a couple shortcuts I had to take there. But yeah, so that's kind of how the software, the fan stuff works. There's a simple function, which I also have, that is basically like a fan curve implementation, this GPU temperature to cooler power. It's hard-coded numbers. If you want to parameterize them, you can, but for my application and just for wanting to be done with this, I just hard-coded them. So I tried PID to do control, but the problem was auto ranging is tough with that, making the set point, making the system aware of, we really care about two modalities, idling and then under load. The GPU or the cooler has no idea when either of those modalities has been like reached or not. So it was hard to implement that with PID, so I kind of bailed on it. So it's just a regular fan speed controller. So the last thing I want to talk about is the timer functionality. So these timer things are great, these that MicroPython exposes. So these are basically a way to execute an arbitrary callback function on a period of time. So I have it so every 15 seconds it updates the fan speed. So and it can do this in the background, right? So these callbacks get called somewhere. I don't really know how it happens, but that means, so this is a Raspberry Pi which is connected to the Pico. So I have a picture. So the Pi right here is connected to the Pico. You can see the wire coming in on the top left there. So we can REPL in real time, and we can tweak, we can do development in a REPL in a running system on an embedded processor, which is so much fun. So I have this read thermistor one shot. So it's on pin 26, the thermistor, and it'll get, like, this is the current temperature in Celsius for that thing, for the thermistor. So you can just keep calling this. You can do while true, using a loop, read thermistor, read thermistor, temp 1, shot 26. Oh, I want to do sleep here. Whatever. Read. Oh, it's not. Okay, so from. Alright, whatever. So my Wi-Fi is messed up because I've got the camera streaming over it, but you get the idea. Like, you can do all kinds of stuff in this REPL on the running system, which is so cool. So made debugging and tuning today very easy. So on the requirement of the full load thing, here I have it all running. So these are the 4 cores running. Each of them are oversaturated, overpowered to 175 watts. I have 4 jobs that are consuming all the GPU they can. So these are 4 real loads that I'm doing for my application. And it's going, and it's working really well. I got a video feed. So that's what the inside of it all looks like live. Yeah, and that's the project. That's the cooler. Like I said, there's going to be a blog post in the description of this video. Everything will be up on GitHub, of course. And if you couldn't tell, I am currently live on Twitch while I'm recording this video. This is the first time I've worked on a project like this live. I did this entire design live on Twitch, and it's been a really cool experience. More than once, people have had like really awesome feedback points on how to improve the design, etc. People coming in with like papers on what I should consider in like the curves of the cooler, or different like how there was a guy that popped in that used the K80s at work all the time, and they had a bunch of different stories about how they have to cool them, because a lot of people are, if you search NVIDIA Tesla K80 cooler, you'll find a lot of people that have published designs. Unfortunately, though, I couldn't find any that had like the stackable configuration, which is why I had to roll my own here. But it's been an amazing thing, and if you are interested in that kind of thing, I'll probably be doing a live design like this again. So I did the whole thing, the mechanical, electrical, and software all live, which was really fun. Okay, so 25 minutes. That's very long, but whatever. Cool. Thanks for watching. Like I said, check out the blog post in the description. Peace.